Hey, Adam, you're on mute.
Hi, everyone, and welcome. My name is Adam Pintar, and I'll be your MC for this webinar. Please remember to silence your microphones and to minimize background noise. Obviously, I forgot to unmute mine before I started speaking, so, that happens sometimes. If you have a question, please use the raise hand feature or the chat box, and I'll be monitoring that throughout, and so will our speaker. The Fall Technical Conference is sponsored by 4 groups in 2 professional societies, the Chemical and Process Industries Division and the Statistics Division in ASQ, and the section on Physical and Engineering Sciences, and the Quality and Productivity section in the ASA. The goal of the conference is to help connect researchers and practitioners of statistics. And in 2013, the conference was in Gaithersburg, Maryland, and it was at 63rd year of the conference. However, an in-person conference was not possible in 2020, of course, because of the pandemic, so that 2 full years did not pass without any FTC activities at all. A series of webinars were organized around the 2020 award winners. The schedule is on this slide, and this is the 5th week out of 6. The last webinar will be a week from tomorrow on December 18th. The presentation today will be given by the Schul Award winner. The Schul Award was first presented in 1969 in memory of C.T. Tiny Schul, former director of ASQC, to recognize his work in applied statistics and analytical chemistry. Tiny was remembered as a big jolly guy whose laugh often dominated the Gordon conferences. The award is given to presenters from the previous year's conference. There are 2 criteria. The heaviest weight is placed on the oral presentation, judged by attendees of the conference through surveys that they filled out. Written material that's submitted to award committee is also considered. The award committee members this year are Brooke Marshall, Stephanie DeHart, Amanda Yoder, and Willis Jensen. Brooke chaired the committee. Thanks to the committee for all of their service and hard work. And the winners from the 2019 FTC are Peter Goos and Jose Nunez for OMARS designs, bridging the gap between definitive screening designs and standard response surface designs. Congratulations! Peter Goos is speaking today. He is a full professor at the Faculty of Bioscience Engineering of the University of Leuven and at the Faculty of Applied Economics of the University of Antwerp. He teaches courses on statistics, probability, and design of experiments, the last of which is his main area of research. He has published many journal articles as well as 4 books. Peter has also received the Ziegel Award and the Statistics in Chemistry Award from the ASA, the Young Statistician Award from EMBUS, the Lloyd Nelson Award from ASQ, and he has also received this award, the Schul Award, previously. Let me conclude my introduction by saying that Peter has been a long-time contributor to the FTC, both presenting and teaching short courses regularly. Thank you, Peter, and I will turn the floor over to you now.
Thank you, Adam, for the introduction. I will now try to share my screen. And of course, good evening to those of you who are in Europe. Good afternoon, good morning to those of you who are in the United States. So today I will present my winning presentation from the FTC the previous year on OMARS designs. Here we go. So OMARS designs bridging the gap between definitive screening designs and standard response surface designs. And I should of course mention that the presentation was based on joint work with my collaborator Jose Núñez Ares. This is Jose here on the next slide. So Jose did his PhD under my supervision, and he is now still a postdoctoral collaborator 3 years after finishing his PhD. OMARS designs are a kind of response surface design. And you all know that response surface designs are experimental designs used for process optimization. They allow the study of several quantitative factors. More specifically, they allow us to estimate the main effects, the quadratic effects, and the two-factor interactions of the quantitative factors in our experiment. And the best known of these response surface designs are undoubtedly central composite designs and Box-Beinken designs. Now, some of the nice properties of these well-known response surface designs can be visualized in a color map on the correlations of the columns of the model matrix for these designs. And one nice feature, for example, of these response surface designs is that they are orthogonal for the main effects. And you can see this in the top left corner of the color map on the correlations. Another nice feature is that there is no aliasing whatsoever between the main effects and the second order effects in such a classical response surface design. In addition, the interaction effects can also be estimated independently from each other, and they can also be estimated independently from the quadratic effects. All of this is nicely visualized in a color map on the correlations. So these are, some nice and attractive properties of classical response surface designs. Here on this slide, I summarize these nice orthogonality properties once more. Main effects are orthogonal to each other, main effects are orthogonal to two-factor interactions and to quadratic effects, and two-factor interactions also orthogonal to quadratic effects. Another nice feature, which is not visible in the colored map, is that these designs offer large powers for detecting main effects and two-factor interactions, but there's also a drawback, and that is the run size. The number of runs in such a classical response surface design increases pretty rapidly with the number of factors under investigation. But if you can afford the large number of runs in such a traditional response surface design, in the end, you have a painless data analysis, so you can easily fit the full quadratic model, and you can easily identify important main effects, interactions, and quadratic effects. The downside is the large experimental costs. At the other side of the spectrum, you could say, we have the definitive screening designs. Definitive screening designs are three-level experimental designs, pretty recent ones, initially intended for screening large numbers of quantitative factors. The fact that they are three-level screening designs makes that you can quantify quadratic effects using this kind of screening design, in addition to the main effects and the two-factor interactions, which you can also quantify from more classical two-level screening designs. Definitive screening designs are pretty new, pretty recent, as I said. They were introduced back in 2011 by Bradley Jones and Chris Nachtsheim in a Technometrics article. And 1 year later, a fast construction of definitive screening designs was presented by Xiao, Li, and Bai in Journal of Quality Technology. And that fast construction method is now the standard construction method for definitive screening designs. And all definitive screening designs that are used nowadays and that are available in commercial software, they are all based on that fast construction technique. Well, definitive screening designs, here's an example of an 8-factor definitive screening design. Most of you probably know that definitive screening designs involve mirror image pairs. So we have pairs of runs which are each other's negative. In addition to that, in a definitive screening design, we have zeros in every column for every factor. And as a result of that, we can quantify quadratic effects. And a definitive screening design, the standard definitive screening design always has at least a center run. And here for the 8-factor definitive screening design, that is the 17th run. These definitive screening designs also have nice orthogonality properties, which can of course also be visualized in a color map on the correlations. And you can see in the top left corner of the color map that the main effects in a definitive screening design are also orthogonal. In addition, the main effects are orthogonal to the second order effects. And that's where the very good news stops, because you can see that when you use a definitive screening design, the interactions are no longer orthogonal to each other. And you can see in the color map, in the central part of the color map, that there is quite a lot of pink for this particular 8-factor definitive screening design, meaning that quite a lot of 2-factor interaction pairs are pretty severely aliased with each other. You can also see that there is some aliasing between the 2-factor interactions and the quadratic effects when using a definitive screening design. To summarize, definitive screening designs also have nice orthogonality properties, but fewer than the traditional response surface designs that I discussed initially. In definitive screening designs, main effects are still orthogonal to each other, and main effects are also orthogonal to 2-factor interactions and to quadratic effects. And for that latter reason, people say that definitive screening designs belong to the class of minimally aliased designs. So main effects are orthogonal to second order effects, therefore they are minimally aliased designs. But we've seen that, you know, not everything is good news in definitive screening designs. In certain definitive screening designs, we have strong aliasing between 2-factor interaction pairs, and sometimes these 2-factor interactions are also severely aliased with quadratic effects. There's one other advantage which was not visible in the colored map for definitive screening designs, and that is that they are very economical in the sense that the number of runs, the run size of a definitive screening design is on the small side, on the very small side, because the run size increases only linearly with the number of factors. But because the number of runs is so small, some aliasing between a higher order effects is inevitable, I would say. Another thing should be said about definitive screening designs, and that is sometimes they are marketed as a screening design and a response surface design in one. And the reason for that is that if the effect sparsity principle holds, if only a few factors matter, then the definitive screening design projects onto a response surface design in those few factors that matter. And so if you're lucky and there's only a few important factors, then you don't need to do a follow-up design because you have your response surface design immediately, you know, embedded within the definitive screening design, you could say. So therefore, you could view a definitive screening design as the smallest kind of response surface design out there. But there's, of course, a major difference with the classical response surface designs. While classical response surface designs like central composite designs and Box-Beinken designs involve more than enough runs to fit all the effects you're interested in, definitive screening designs by far do not have enough runs to estimate all the second order effects on top of the main effects. And because of the small size of definitive screening designs, the analysis can be quite painful if you have bad luck and more than a few factors matter and more than a few second order effects matter. So you may be left with ambiguity concerning which effects are significant, especially if more than a few second order effects matter. So that's the price, of course, that we pay for the small size of definitive screening designs. Another thing is, there's only a limited number of definitive screening designs out there. They exist only for certain numbers of runs, for certain numbers of observations. So to conclude this introduction, on the one hand, we have traditional response surface designs with great properties, but a lot of runs. On the other hand, we have DSDs with a very small number of runs and with some attractive properties, but also some unattractive properties. Now, what José wondered during his PhD was, would there be similar designs? Would there be designs with similar orthogonality properties, but somehow with intermediate numbers of runs? Well, José started looking for these designs that bridge the gap between definitive screening designs and traditional response surface designs, and he discovered a whole new family of designs that do fill that gap. And that new family of designs, we had to give it a name, of course. Your child has to get a name. And we called the new designs orthogonal, minimally aliased response surface designs. In short, or abbreviated, OMARS designs. And why do we call them that way? Well, OMARS designs have 3 levels per factor, and they are intended for quantitative factors. We study 3 levels for each factor, and because of that, we call them response surface designs. So that's where the RS comes from in OMARS. In addition, the main effects are orthogonal to each other in OMARS designs. So that's where the O comes from orthogonal. And finally, there's still the MA to be explained. Well, in all the OMARS designs, the main effects are orthogonal to the 2-factor interactions and to the quadratic effects. So OMARS designs also possess the minimal aliasing property, so we can call them minimally aliased. So orthogonal, minimally aliased response surface designs. And what's not in the name of OMARS designs is the following. All our designs have our original OMARS designs have a uniform precision property, in the sense that all the main effects can be estimated equally well, and also all the quadratic effects can be estimated equally well. So that's, there's uniform precision for all the main effects, and there's also a uniform precision for all the quadratic effects. Now you may wonder, how big is that family of OMARS designs? Well, here you can see the table that shows the number of OMARS designs which we discovered initially. In the table, in the first row, you can see the numbers of factors for the different OMARS designs we initially discovered. In the second row of this table, you can see the number of runs of the OMARS designs we initially found. And then in the next row, you can see how many different OMARS designs we found for 3 factors, 4 factors, 5 factors, and so on. And you can see that, the larger the number of factors, the more OMARS designs we discovered. Most of the OMARS designs we found have an even number of runs, and of all those OMARS designs with an even number of runs, the vast majority also has fold-over pairs or mirror image pairs, just like in the definitive screening designs. So we have these pairs of runs which are each other's negative. That's the majority of the OMARS designs. But we also found OMARS designs with even numbers of runs which do not belong to that family of fold-over designs. And we consider these OMARS designs extra interesting because it is well known that designs that are not fold-over designs, they provide you more information about interaction effects. So you can estimate more interaction effects if your design is not a fold-over design. But there are fewer of these non-fold-over OMARS designs. And we also found a few OMARS designs with odd numbers of runs. So you can see that we found various kinds of OMARS designs. And of course, OMARS designs with odd numbers of runs are by definition not fold-over designs. So they are also extra interesting. So in the end, we have quite a lot of OMARS designs. We found a lot of OMARS designs in our original study. How did we do that? Well, to understand how we found the OMARS designs, you should know perhaps a little bit of the background of José. José has a background in operations research. So yeah, he's very good in linear programming, integer programming, that sort of thing. José found all the original OMARS designs using integer linear programming approaches. More specifically, José set up systems of linear equalities for every number of runs and every number of factors he wanted to tackle. And if you solve the system of linear equalities that he set up, the end result, the solution of it, is an OMARS design. Now, whenever he found an OMARS design, he added some constraints to his original system of linear equalities to make sure that if you solve the original system of linear equalities plus the extra constraints, you find a new OMARS design. So then he solved a slightly different system of linear equalities that gave him a new OMARS design. And the new OMARS design is different, and in the jargon we say it's not isomorphic to the original OMARS design found. And this procedure was repeated, every time José found a new OMARS design, he changed his system of linear equalities to make sure you find a new OMARS design over and over again. Now, at some point in time, this procedure stops. At some point in time, his system of linear equalities is no longer feasible. And when that happens, you know for sure that you have found all the non-isomorphic OMARS designs. And of course, there's a lot of computing time that went into solving all these systems of linear equalities. But the end result was a rich family of new response surface designs. A few technical things, perhaps. The initial OMARS designs that we created that way did not have center runs. And why is that? Well, if you have found an OMARS design, then you can add as many center runs as you want, and the OMARS design will keep its nice orthogonality properties. So an OMARS design with one or more center runs remains an OMARS design. During his enumeration of OMARS designs, José rediscovered the DSDs, the Box-Binken designs, the central composite designs. So his family of designs generalizes the existing sets of response surface designs. And the end result is basically a whole new catalog of response surface designs with similar attractive properties as the well-known CCDs, BBDs, and DSDs. If you want to read more about the enumeration and some of the technical properties of the designs, I can refer you to an article which has appeared recently in Technometrics about that original enumeration of OMARS designs. Since the publication of that Technometrics article, a lot has happened in the OMARS world. José has kept on improving his enumeration techniques, and in the meantime, he's found many more OMARS designs for larger numbers of factors. And I'm not sure whether you can see my pointer here. I will do it that way. I hope you see my pointer. Well, here's the number of factors in these new tables on the current slide. 6, 7, 8 factors. Here we have the different numbers of runs. And you can also see the number of solutions to the linear equality systems of José. And you can see that, for 6 factors, 7 factors, 8 factors, José found quite a lot of OMARS designs with up to 30 runs here. And on the next slide, we go up to 40 runs. And so you can see that for certain cases, there are more than 200,000. Here there's more than 4. Here there's 16,000 OMARS designs, 57,000 OMARS designs for certain cases. So our family of OMARS designs is getting richer and richer by the day as our supercomputer here in Leuven is solving systems of linear equalities. If you carefully study the table, you will see that we find more OMARS designs for even number of runs, for even numbers of runs than for odd numbers of runs. So that's something we see over and over again. But overall, we have many OMARS designs for quantitative factors here. Of course, a lot of computing time went into that. You can see that, like here we have 20 years of computing time, 25 years of computing time. So we certainly didn't find these OMARS designs very easily. Now, enumerating designs is one thing, but of course you always hope that you enumerate good designs or that you find good designs. So you may wonder, are these OMARS designs any good? Well, to give you a flavor of the qualities of OMARS designs, I have a few examples here in the presentation. There are some more examples in the Technometrics paper. And to show or to try to convince you that the OMARS designs are good, I will use benchmarks throughout the rest of the presentation. And the benchmarks are always definitive screening designs. And the reason for that is that, definitive screening designs are the only benchmark design out there in the literature. It's the only competing design, you could say, that has similar orthogonality properties as the OMARS design. So it's definitely not that I dislike definitive screening designs, but you need a benchmark when you want to show that what you've discovered is good somehow. First example, the 22-run 5-factor OMARS design from our Technometrics paper. I will compare that one with a 22-run 5-factor definitive screening design involving 2 center runs, constructing using jump by asking for 8 extra runs. So I exploit here some of the capabilities of jump to construct a benchmark design with the same number of runs as the OMARS design. Well, if we compare the two designs, then we can see that the OMARS design is able to estimate all the two-factor interactions, while the definitive screening design is not. So the OMARS design provides more information, you could say, about the two-factor interactions. If only a few factors matter, then the OMARS design also has better properties to estimate models involving these few factors. So we can say that the OMARS design has better projection properties than the definitive screening design. And another positive feature of the OMARS design is that it has a much larger power for the quadratic effects, of course, at the expense of something else. The larger power for the quadratic effects comes at the expense of a slightly smaller power for the main effects, and I should also add a smaller power for detecting certain interaction effects. Here's a plot showing the powers for detecting main effects of the 5 factors and quadratic effects of the 5 factors. And in this plot, the blue bars are the powers for the OMARS design, and the purple bars are the powers for the definitive screening design. And you can see that the blue bars are substantially longer for the quadratic effects, but they are a bit shorter for the main effects. In terms of average variance of prediction, the OMARS design also does better than the definitive screening design. So here you can see the prediction variances that you get for the model with main effects and quadratic effects for the OMARS design, blue line, and for the definitive screening design, purple line. And since the curve for the OMARS design is lower than the curve for the DSD, we have smaller prediction variances with the OMARS design. And we can, of course, look at color maps on the correlations. On the left-hand side, you can see the color map on the correlations for the OMARS design. On the right-hand side, for the definitive screening design. And you can see that the definitive screening design has a few pretty dark pink cells in the central part of the color map, meaning that certain pairs of two-factor interactions are pretty strongly aliased. That does not happen in the OMARS design, but in the OMARS design, I should also say that there is some light pink here, indicating rather strong aliasing between certain two-factor interactions and certain quadratic effects. But on average, the OMARS design has smaller average correlation between second-order effects than the definitive screening design. So in terms of aliasing, the OMARS design is better than the definitive screening design. So that's at least one good OMARS design, I dare say, and that's the design. Which is a fold-over design. You can see that the first row in the table is the negative of the last, the second row is the negative of the one but last, so it's a fold-over design. It's balanced as a result of that, of course. There's as many +1s as -1s in every column. No center runs in this particular OMARS design. And there are 6 zeros in every column. And because of that, there are more zeros in every column for the OMARS design than for the definitive screening design. And that explains why the power for the quadratic effects is bigger for the OMARS design than for the definitive screening design, and smaller for the main effects. And due to this fold-over nature, the OMARS design can be blocked orthogonally in 2 blocks of 11 runs. So these are some of the properties of the OMARS design. You could say that this is a rather small OMARS design. This is one coming from the Technometrics paper from our first effort to produce OMARS designs. Here is an OMARS design, or at least the color map of it, of an OMARS design from one of our most recent efforts. This is an OMARS design which we needed in a consulting project for an energy producer. This is the color map for a design, an OMARS design with 10 factors and 27 runs. So quite a lot of factors and only a limited number of runs, 27. And you can see that there is no major aliasing. There's no major aliasing among the two-factor interactions. And yeah, here's some more details about that design. It's a design in which the 3 levels of the 10 factors are replicated equally often. And that means there's quite a lot of zeros in this OMARS design. And therefore, there's a large power for detecting quadratic effects. The OMARS design also has very good projection properties. For example, the OMARS design here allows you to fit any response surface model in any 4 factors. And that's unlike all the benchmark definitive screening designs we tried with similar numbers of runs. And therefore, you can say that, you know, for 4 factors, the OMARS design has a 100% projection estimation capacity, and benchmark definitive screening designs we tried only have a projection estimation capacity of 33 and 73%. So that means definitive screening designs can only estimate 1/3 of the response surface models in 4 factors, and 73% for the other benchmark definitive screening design. So here again, we see that we have a nice small response surface design with quite good properties when you compare it to designs available in the literature, in this case, definitive screening designs. When you look at the powers, here I have a picture for the powers of the OMARS design and the 2 benchmark definitive screening designs that we used. You can see at the bottom right that one DSD we tried has 25 runs, the other DSD we tried has 29 runs. And you can see that for the quadratic effects in this picture, the blue bars for the for the OMARS design are much longer than the bars for the definitive screening designs. We give in a little bit on the main effects in terms of power, and we give in a little bit more when it comes to interactions. But this is for quite small signal to noise ratios. As soon as you increase the signal to noise ratios somewhat, the powers for the OMARS design are equally big as the powers for the benchmark definitive screening designs. And you can see that for the quadratic effects, the OMARS design keeps on outperforming the DSDs even for larger signal to noise ratios. So we see once more that we have a second good OMARS design here in this presentation. And in the meantime, you can also find OMARS designs with 13, 14, 15 factors. And here you see the color map for one of the 13-factor OMARS designs we found. And you can see that the color map is very similar to the color map for a benchmark 13-factor definitive screening design. So you can see that the OMARS designs are indeed pretty good, certainly when compared to the definitive screening designs. And you should realize that here I just show you a few OMARS designs for numbers of runs that match the definitive screening designs, but we have many more OMARS designs for many different numbers of runs for each given number of factors. Yeah, and since we have a lot of OMARS designs, you know, you may think, yeah, if you have so many OMARS designs, how do you know which one is the best? How can we choose a design from that large catalog of OMARS designs? Well, we characterized all the OMARS designs we have in many, many different ways. Classical optimality criteria like D, I, A optimality. We calculated powers for detecting main effects, interaction effects, quadratic effects. We calculated standard errors. We computed projection estimation capacities to see how good the definitive screening designs are for fitting models with 2 factors, 3 factors, 4 factors, 5 factors. So basically, we turned the OMARS designs inside out to quantify all their properties. Basically, we tried all design selection criteria that are available in the literature, or almost all, I should say, to try to find which ones are the best. And because we know all or a lot of properties of the OMARS designs, we can basically select OMARS designs taking into account multiple criteria. So we can basically use a multiple criteria approach to select designs now. A major criticism to optimal design of experiments is that your designs are only optimal for one criterion. Well, now that we have this catalog of OMARS designs, we can select designs taking into account many, many different criteria. And to make this practically feasible, we are working on a web-based application to do that in a user-friendly way. How does that look like, that web-based application? Well, it involves 3 stages: a satisficing stage, a dominance stage, and then finally the final selection of the design. In the first step, the satisficing stage, we basically select designs which meet certain acceptability criteria. We say things like our projection estimation capacity for 4 factors should be at least this high. Our power for quadratic effects should be at least that high. The prediction variance should be at most this. You know, we can basically impose a lot of wishes on the designs. And the designs that survive our initial acceptability criteria, they enter the second phase, the dominance stage. And in that dominance stage, we get rid of all the designs that are dominated by others. And in the jargon, we say that in this phase, in the second stage, we basically select the designs that are Pareto optimal with respect to the criteria we are interested in. And as soon as we have the non-dominated designs, so the Pareto optimal designs, as soon as we have these, then we enter the final stage. And in that final stage, we can do 2 things. If there are many Pareto optimal designs, then we use the utopia method. And the utopia method is well known in multi-criteria design selection, I would say. The utopia method basically selects the OMARS design that's the closest to the so-called utopia design. And the utopia design is a sort of fictitious design, which is the best in every criterion you have in mind. And the OMARS design that approaches the utopia design the best, well, that's considered the best of all the Pareto optimal designs. If you follow that approach, if you follow the utopia method, you have a sort of automatic selection of the best Pareto optimal OMARS design. Now, if you only have a few Pareto optimal OMARS designs, well, then you can, of course, in our web-based application, also manually compare those few OMARS designs you have left. And then you, as a design expert, you can compare manually the OMARS designs in terms of your favorite criteria. So that's, the design selection that you can do once you have a catalog of designs. So to summarize all these contributions, we created a brand new catalog of orthogonal response surface designs, and we've seen that the OMARS designs certainly challenge the definitive screening designs, but yeah, we have really quite a lot of OMARS designs with more runs also than definitive screening designs. So really we have OMARS designs that bridge the gap between definitive screening designs and response surface designs. So therefore, the family of OMARS designs offers a lot of flexibility in terms of the number of runs. And in our view, the OMARS designs will be especially useful when your number of runs is too small to estimate simultaneously all the main effects, all the interactions, and all the quadratic effects. So the OMARS designs are especially useful in situations where classical optimal experimental design, D-optimal design, I-optimal design is not feasible for the full quadratic model. And another thing is, I showed that as well, the availability of this complete catalog of OMARS design allows us to take many different criteria into account when picking a design and to develop a whole new way of selecting designs in this web-based application. Now, we haven't sit still since, the generation of all these OMARS designs, which I presented to you, because you all know that there are many experiments in which the experimental factors are not all quantitative. There are many experiments where you also have one or more categorical factors. And the combination of traditional response surface designs and categorical factors has not received very much attention in the literature. Almost the only thing that has happened in the literature is that definitive screening designs have been extended with two-level categorical factors to tackle experiments with both quantitative and categorical factors. But the DSDs with two-level categorical factors that are available in software nowadays, they are no longer perfectly orthogonal. So you lose that beautiful color map feature, you lose the perfect orthogonality between the main effects. Well, our initial computations show that there are quite a lot of OMARS designs that can be extended with one or more two-level categorical factors without losing the attractive orthogonality property. So we score better in this respect than these DSDs. And so we found quite a lot of OMARS designs with two-level categorical factors on top of the quantitative factors. And this figure gives you a flavor of what kinds of OMARS designs we found with two-level categorical factors. On the vertical axis, you can see the total numbers of factors of the designs we found. On the horizontal axis, we show the numbers of runs for which we found OMARS designs with two-level categorical factors. And in the figure, you can also see three symbols. The three symbols refer to three different construction methods that José tried to enumerate these OMARS designs. And you can see that, all the numbers of runs in this figure are multiples of 4. That is because you can only find OMARS designs with two-level categorical factors when the number of runs is a multiple of 4. And you can see that we found certain designs with up to 22 factors. So at the top right of the figure, you can see the horizontal symbol indicating that we have designs with 48 runs and up to 22 factors in total. So some of our OMARS designs are really not small. They're actually quite large, and they allow you to study many different factors. Our OMARS designs with two-level categorical factors are also quite good, as illustrated by this slide. On the left-hand side, you can see the color map for a 20-run OMARS design, 6 quantitative factors and two-level categorical factors. And you can see that among the two-factor interactions, there is no severe aliasing. There is some serious aliasing going on between interactions and two-factor interactions. But if you compare the OMARS design to one of the DSD benchmark designs we created, well, then you can see that in terms of aliasing among the two-factor interactions, the OMARS design does better. We also constructed another benchmark definitive screening design by exploiting all possible options that are available in JUMP. The second benchmark design we managed to construct doesn't have the same kind of severe aliasing as the first benchmark, but if you look closely, you can see that there is also some pink here, some pink also indicating severe aliasing or serious aliasing among certain interaction pairs. And if we compare the average correlation between the second order columns of the model matrix of these 3 designs, then the OMARS design scores best in terms of this criterion, the average correlation between second order effects columns of the model matrix. So here again, you can see that the OMARS designs, also those with two-level categorical factors, have certainly merits. And then the final thing I want to mention, I didn't keep an eye on the clock, so I hope I didn't talk too long. The final thing I want to mention is that all the OMARS designs I've discussed so far offer the same prediction for the main effects of the quantitative factors and for the quadratic effects. In one of the most recent efforts that he made, Jose also tried to construct OMARS designs that do not possess that uniform precision property. And it turns out that there are quite a lot of these designs. And you may wonder, why is this useful? These non-uniform precision OMARS designs, well, we believe that these designs are useful, especially in scenarios where for certain quantitative factors, you do expect quadratic effects, while for other quantitative factors, you may not expect quadratic effects. So by offering also non-uniform OMARS designs, we have a new kind of approach to tailor the OMARS designs to any needs that the practitioner may have. And that's the last thing I want to say. I would like to thank you for your attention.
Thank you very much, Peter. We do have, so I think you're doing very well on time. We have several minutes left for questions. If anybody has questions, you can put them into the Q&A or the chat.
And I will try to find the chat so that I can read the questions, perhaps.
You have to move the cursor down towards the bottom. It should appear then.
And unfortunately, it doesn't.
Okay.
But if I press escape, then hopefully I'm more successful.
Okay.
maybe I should, I don't know, stop sharing because I...
Okay. We do have one question. Would you like me to read it, Peter?
Yeah, I think I can read the question now. Do OMARS designs have a special analysis like DSDs have in JUMP? And the answer is yes. We are working on an article about that. So the special analysis that's available in JUMP, yeah, it is of course very powerful for DSDs. You could literally apply the same kind of analysis to our fold-over OMARS designs, but we hope that in our article we can still do better than that analysis technique. So we think we can still offer a bit better power by an even more specialized analysis for OMARS designs. But that is, you know, yet to come out in an article. We haven't presented that work yet.
There are a couple of questions in the chat window as well. Peter, can you see that? If not, again, I could read those.
Yes. So one question I can read there from Catherine is, do you know if these will be available in JUMP in the near future? Well, I don't know that. Of course, the developers of JUMP are aware of the OMARS designs, but right now there are no concrete plans as far as I'm aware of. But yeah, we are working ourselves on this web-based application to make OMARS designs available. So maybe you won't need JUMP to find OMARS designs. Question of Brad. Do you have a sense of how many more than 2k plus 1 is a good guide? So 2k plus 1, that's 2 times the number of factors plus 1. That is the size of a standard definitive screening design. Brad, you are probably aware that in the literature it's now recommended to do a few extra runs on top of the standard definitive screening designs. I think that's even the default in JUMP software, to do 4 extra runs for definitive screening designs. How many more than 2 times k plus 1 is good in general? I find it very difficult to give a general answer, because it of course depends on the variability in your system that you're studying. So I would always calculate powers, taking into account as much as possible all the information you have about your system. Also, you know, how many significant effects do you expect? How many interactions do you expect? So that's a hard question to answer in general, I'm afraid. But the nice thing about our catalog of OMARS designs is that you can quantify the benefits of increasing the run size pretty well. In the meantime, I see in the Q&A that new questions are coming in. Is the web selection tool available now, or do you expect it soon? Yeah, we are working very hard on that. Yeah, we hope that in March, April of next year, we are close to presenting our web-based tool. But you know, if you have thousands of designs, many criteria that you want to use to select a design, that is definitely non-trivial to make available in a user-friendly way. But we're working hard on achieving that. Steve, how are the powers to detect different effects calculated? From which model? The powers that I presented today, I suppose. Well, the powers were calculated for the models that had all the effects in the picture. You know, in our web-based application, we calculate powers in many different ways, like if you fitted all the main effects, what's the power for detecting one extra quadratic effect? Also for detecting one extra interaction, but we also quantify, you know, powers if more interactions are in the model. So we do it in various ways. But what I presented today was quite simple. So I showed you one picture with powers for a model with main effects and quadratic effects and nothing else. And in the other picture, I had all the main effects, 2 randomly selected quadratic effects, and 2 randomly selected interactions. And the powers were calculated for these models. Any other questions?
Does not appear so at the moment, and it looks like we're just a couple of minutes after 4. So thank you, Peter, again very much for a very good talk. I enjoyed.
You're welcome.
And I guess we shall conclude for today.